click it. Yeah, and then any load case is okay. Let's check the moment diagram and say apply. So you're gonna check the moment diagram, right? We even practice hand calculation. Yeah, too many decimal points. Oh, 4 decimal point. You can just go and reduce the decimal too much. The bottom one, bottom one. Okay, here fourth, you can make it 0 or 1 here. Yeah. Maybe 1 1 1 or 0. This up to you. Make a moment forces 1. Yep, say. So this is a moment at the middle span, right? This is dead load cases, so it's a self weight. Self weight of the slab, self weight of the steel beam. So they consider it. So I think let's check the what kind of slab did you use it. Go to define and section and deck section. So yeah, click it open. So using 3-inch metal deck and 4.5 inch concrete. So normal weight 4,000 concrete. Okay, so that being said, again, we should be able to calculate this, right? 3-inch metal deck and 4.5 inches. So 3-inch metal deck, 4.5 inch metal concrete topping. So when you make this a flat, equivalent flat, the depth of the concrete, obviously 3 inches divided by 2 plus 4.5 inches. So this is what? Total 6 inches, right? So total 6 inches divided by 12 is, yeah, basically zero point 0.5 feet times, if this is concrete material, I think default my using 150 pound per cubic foot. So you don't need a calculator. It's about 75 PSF. Slab weight is 75 PSF, right? You understand this, right? And we here you see the metal deck default weight plumb. So maybe we can add it 2.3. So total slab weight is 77.3, right? 77.3. And still, I don't know what sizes we are ending up, but we can roughly calculate it. So tributary width is 10. This is 77.3. So roughly 77.3 times 10 feet. So this is a point, I'm gonna just, okay, 0.773 cube foot, right? So roughly self-weight of beam, for now exclude, we'll roughly check this, whether this number is reasonable or not. 0.773 times, is the length is 45 feet?
Yeah.
Yes, 45 square divided by 8. So I have 195. So if you calculate this bending moment, 195.6 kip foot didn't include the beam weight. So if you include the beam weight, I think this number is going to be most likely matching, right?
Yeah, that's what I got.
Yeah. So this is what yes. Yeah, we learn it. WL square divided by 8 for uniform line loading, right? So now, so the reason why I showing repeat this, just first of all, when you run it, because we always make a mistake or miss, so we need to check the bending moment diagram is reasonable. Single curvature bending moment diagram, yes, right? And Goddard, because eventually we're gonna have a 2-point loading. So this Goddard is receiving this 2-point loading from the beam. So the bending moment diagram is like this, trapezoidal, which makes sense. All right, so it seems like while you're checking overall geometry and connectivities seems reasonable and makes sense, we didn't make a mistake, then you're moving into the design. So let's go back and go to design, hit the design. We close this and go to composite beam design module, right here, and start design check. All right, so this is what ETABS gave us, same thing, 21 by 50. We're gonna discuss briefly one more time. The one thing you need to aware of this, because I'm sure you guys actually learn the beam design in the steel class. I think we probably learned the umbrace length, right? Umbrace length L sub B. So beam is spanning from here to here, right? If we don't have any bracing, this beam's umbrace length is as long as 45 feet. But since we tie the concrete with a stud, right? The steel beam is secure to prohibiting from the torsional buckling. Is torsion rotating, right? Lateral torsional buckling is eliminated because of this cut. Basically, with the stud, and then concrete and steel is fully, combined, glued together. So this composite connections of stud and concrete is going to provide a lateral bracing. So we assume this is a continuous lateral bracing, so that L sub B is almost zero or very minor, right? It's umbrace length L sub B, right? All right. So okay, so this is the one everybody actually the mid in the middle term. You need to show typical your current building floor layout, right? Floor layout. You maybe can, if you're really interested to do something more, you can add one more bay, or you maybe want to do this, right? And something like that. You maybe this is something exercise, but obviously, yes, you need to know how to, yeah, divide this, the beams. But obviously, I think rectangular geometry is okay as well. But because at this point, I want you to focus on overall workflow. I mean, more exciting geometries, yeah, need more attention, and you need to spend some time to, draw it and cut it. Yeah, it's up to you, right? But if you want to add a few more, you need to exercise a little bit more. This is about all the drawing, geometry. So you may end up to draw another grid line, grid line, grid line, grid line, and then you need to draw the beam and the gutter and beam with the column as well. So this is something geometry. So, all right. So assume that everybody actually got this. Now, I'm gonna point out again, everybody pay attention. So go to design. Otherwise, you're not gonna keep these sizes. So go to design. Last Once it taps a choose member, go to composite beam. You need to do this. Verify all member. Yeah, click it. So and then say okay, and then rerun it. So that you see the ETABS selected member size, so will be overridden over our original section properties. So you basically update your model, those member size. Okay. Once you run it, go again, they click the design. Budget beam design. Start design check. Somehow it's stuck.
I fear it is stuck, Professor.
Yeah. This is output mode displacements. Then load this. Can you hit the escape? Otherwise, maybe you need to close the tabs and reopen the tabs. Yeah.
Okay, hold on.
Yeah. Okay, what you see, yeah, the member size is updated. Okay, now here, everybody actually think about how to present your design, right? So start with your building floor plan layout. Explain that typically geometry of your project. You have typical building is 1, 2, 3, 4, 5. So 30 by 5 is 150 feet by 45, 45, 30 maybe. So 90, 120 feet floor plate. We have a typical bay is 30 feet by 45, right? You have a central concrete core system, and also the steel column is providing a vertical support. So typical bay 30 by 45 you design, and the typical beams you could click. First of all, this you could click this. So you need to, all the middle term, you need to present that typically you're selling this design, so floor plan, layout, and this is the overall design output. Now you're going into the detail, click it or select and right click. Yeah. So this beam, so this is design output. So you need, so first of all, that we already discussed. So based upon auto selection section properties, ETABS chose those all the beams are the workable, right? The lightest is 21 by 50 to 36 by 130. So obviously the lightest beams 21 by 50 is the most economical beam, but it requires a number of stuff, 41 here. Obviously, heavier beams, right? Going heavier deep beams need a less number of stuff. See it, right? So this is actually 40 or 21 by 50 beams need a shear stud 40 to get the composite action up to 58% composite action. Meanwhile, it need a 2-inch camber to meet the deflection criteria. They're all the ratio for design and substability ratio is reached up to 0.997. So this is summary of all acceptable design member and associated number of stud and required camber. Obviously, big beam, heavier, deeper beam, right? It's because the deflection is not controlled, so they don't need a camber. But obviously, heavier is more cost. So what you could see this is from the lightest to heaviest, which one is available. You can you'll be able to understand this the list summary of the chart. On that, okay, specifically now checking procedure, the strength check and stability check, deflection check, right? So there are two check here and there, right? So as I said, the steel strength check actually they're conducting two phases during the construction phase, phase one and phase two. Phase one is when concrete is wet. Second, phase two is concrete after it's cured. So, so first of all, they calculate the maximum factored shear, right? 64 kips is most likely 1.2D plus 1.6 load combination is governing. So you're sure this beam is 64 kips, but design capacity here 219. So shear is not a really governing case. Your W21 by 50 has a pretty significant shear capacity. Typically, the shear nominal capacity is, I think, number phi VNs roughly zero point 0.9 times zero point 0.6 times F prime F sub Y and your AW area of your web member. So that's a shear capacity. It's hard to say. zero point 0.9 times zero point 0.6 times Fy and a area of web member. So, okay, sure is no issue. Now, bending, construction bending and, right, full and partial bending. So, construction bending is the first one, the phase one. Basically, the steel W21 by 50 is fully contribute to support this, the 1.2 depth plus here. Because of this construction bending means this loading cases 1.2 self-weight of slab, right? And I think we need to check it. I think they may see point either 6 or point 0 construction live road, not full live road, permanent live road, construction live road. So phase one, they have their own load combinations because their loading condition is only they have self-weight of slab, concrete, and construction live road, which we assign 20 PSF. So this is a load combination they use and calculate the maximum anticipating bending moment is smaller, right? Because they using construction live road. So this and their capacity is 413 is pure steel bending capacity. Typically, the beam is fully braced. So phi m sub n, right? I'm sure everybody actually take the steel courses. You know that point F, point 9, Fy, and Z sub x, right? So this is plastic, the bending capacity of this W21 by 50, right? If you're interested, just do some calculation. 0.9 times 50 KSI find out the plastic section modulus of the W21 by 50. Do you have a box with you? 21 by 50. I see 110. Okay, 110. This inch cube. So when you calculate, always the formula, just stay with the same unit. So zero point 0.9 times 50 times 110. So this is divided by 12. So I have a 412.5 kfoot. I think this is actually round up, so 413. So you see that the construction bending capacity is fully raised, so that steel is assumed to fully develop the plastic capacity, so that zero point 0.9 times 50 times z sub x plastic section modulus, right? So the first one, basically stress level is zero point 0.8. Okay, so the ETABS actually calculated and confirmed that these members are okay for during the construction. Now, second, let me close. Okay, we are recording it. Let me close it. Close it. Clean up. All right. Now, here we have a full flexural bending capacity and partial composite bending capacity. So this is the maximum 1.2 that times 1.6 permanent live load, right? So permanent live load, we assign, I think, 100 PSF. It's hard to draw it using mouse. So obviously heavier than just phase one total maximum bending moment because the live load is different. So now this is the true bending capacity we are talking about using partial composite bending, which is 41 number of shear stud, right? And the percentage is they found that we need only composite action of 58%, which required 51 stud, should develop flexural bending capacity up to 793, which is less higher than our maximum bending. So they propose the number of 41 stud, right? But this number, obviously, this composite action, the someone say, can you click this, increase this number? If you increase the number, this one will increase it. Let's say 90%. Or right? So or 100%. You see that number? If you change to 100%, I think it goes to 937. Oh, if you choose 100, oh, well, if you go 100, okay, they turn up. Oh, okay, 99 then. 98. Okay. See this? Right? If you add more stud, which is more composite action, which means physically you really glue together very monolithically as a one member, right? If this stud is more and more concrete and steel beam is working as a one, so you're reaching 100% full composite bending capacity. But this case is we don't need it because our design loading is 716, right? So ETABS is choose recommend go back to 58, automatically propose that, okay, you know what? W21 by 50 is only need 41 shear stud, right? Which is about the composite action 58%. And with a camber, 2-inch camber, it works for strength, shear, right? And phase one bending and also permanent bending. So that this beam is strength-wise is okay. So they propose they summarize all this required number of stud and camber and check the strength check. Is that clear? conceptually?
Yeah.
Okay. Just I think first of all, I want you because sometimes it's too much formula, you're gonna get lost. I want you to just pay attention that physically think about it, right? And if you are interested, we can build some model with I-beam and with some slab as you just glue together. I mean, they stick more solidly and eventually give us the more strength and stiffness, which is actually physics and mechanics they combine. We can understand much clearly. This is, but so there is all mass formula basis. They explain that. So one thing is I want everyone just at least aware of it. Number of studs, more and more, you're gonna get the more composite action. Members, concrete and steels are glued together, work more stiff together, right? Gather together is that we can survive more, better. Because usually gladiator, I think I love that last scene. Stay together, you can survive together, right? So you just utilize the composite action can boost up your strength and stiffness. All right. So this is strength set. So, and what all your teams have to actually address that what kind of beam size and number of stud and camber and stress ratio you come up with. So strength check, you need to elaborate it, okay, based upon ETABS current design requirement, strength check, right? The phase one and permanent condition, we meet that capacity, right? Or at the maximum ratio, stress ratio zero point 0.9 here, right? From the strength standpoint, strength check, maximum stress ratio is zero point 0.9, but here it show 0.997 because this one is ratio from highest ratio among the strength check and deflection check here. So here's, we're going to talk about deflection. All right, now we're gonna move, okay, strength check and deflection check, right? So I assume that everybody aware of deflection serviceability check because any beam design, you need to choose the member size for strength. So bending moment and shear forces, whatever your capacity should be, your capacity, whatever your bending and shear capacity should be greater than your ultimate forces, right? So that's a philosophy, which is safety. It's the common sense. Now, deflection is not strength governing, it's more deflection. So if the beam is deflect too much, obviously the operation, right? So our function of this slab is gonna be nightmare because anything is gonna roll down. Obviously, it maybe could be trip hazard, right? It doesn't do some there proper function. So the building code, kind of have some multiple serviceability check and guideline. First of all, easily you remember that this vertical deflection delta under the live road, we actually limit to span length divided by 360, right? So length divided by 360. So this is live deflection at the maximum span, the deflection L over 360, which is if you have a 30 feet, or let's say 45 feet. This one is 45 feet. So 45 feet times 12 divided by 360. So that's the maximum criteria, 1.5 inches. So here you see the allowable maximum, right? So this is one example, straightforward. So live road deflection criteria, the length divided by 360 should be met under the live road deflection. Now, here, now, so let's go through this we have two phases, phase one and phase two, right? Phase one is purely steel is contributing. Phase two is steel and concrete is fully contributed. So first, phase one is temporary construction phase. Phase two is permanent condition. So that steel, bare steel versus slab and steel composite action. So that is our basic construction phase. We also follow along. So let's see. All right, so let's check this. Okay, shows the distribution. Okay, 41 stud. Okay, I see it. 41 allowable. I think they overall lengths. They because the beam is this, they may be typically allowed. Depends on your flange width. The stud can be maybe could be installed one or two rows or three rows, but I think they check it. Seems like 88 is maximum number of stud we can provide, but 41 is okay. Now pre-composite deflection. Since as we name it pre-composite deflection means this is steel beam deflection due to the dead load. Pre-composite beam. So without any this is based upon the concrete weight due to the concrete weight, how much this is steel, bare steel can be deflect. It show they calculated 2.65, right? So this is the 1 day initial calculation. So this case is whatever this deflection calculation is what? W5WL to the fourth century, what, 84 EI, something like that, right? This uniform deflection formula, but this I, Young modulus is, still Young modulus, 29,000 KSI, and I is from our section, W21, 20 by 50. And the top piece is the loading and so formula. So they calculate as a 2.65, right? So when you pour the concrete, you're gonna have a 2.65 inches deflection. All right, wow, relatively big. Now the post composite deflection is after concrete is cured, right? After concrete is fully cured, so this post composite deflection means we have SDL loading, right? It's a superimposed dead load and also live load to live load due to the deflection due to the superimposed dead load and live load deflection will be 1.14 inches. So because why this is small? Because of the post composite deflection means after concrete is fully cured, right? So I value is not bare steel, it's a composite I. Moment of inertia, ooh, they use a composite the I value. So this one is much higher. So deflection is relatively small. So that's why we try to use composite action because we gain pretty significant stiffness increase. So here 1.14, right? And here library deflection, basically just this is library deflection, which means under the I composite, their library deflection, they calculate zero point 0.9, which is smaller than deflection due to the STL plus library, which is makes sense, right? So those are all calculation. Now here is showing since total deflection when you sum them up, pre-composite deflection plus post-composite deflection, right? When you add them up, 2.65, let me just punch the number. 2.65 plus 1.14. So it's 3.79, right? But they suggest 2 inches camber. So it's a upturn camber. So you need to subtract back. So total deflection, downward deflection, most likely 1.79, which is 1.8, right? So this is showing total deflection minus camber. Obviously, this summation of these two minus 2 inches, so 1.8. So this is, you could think of it, initially beam is upturn, camber, When you pour the concrete, it's gonna level it, and SDL and lively deflection, it'll go like this, right? So we try to use the camber to offset the self-weight deflection mostly, so that most of deflection under SDL and live road is something the we are more pay attention. So this calculation explained that the concept of camber, right? Basically, we camber up, the bend up, so that we try to minimize total deflection by using camber. So here 1.8 versus total deflection here, criteria is total deflection is typically, I mean, deflection due to the dead plus live load is try to minimize less than L over 240. So live load deflection is L over 360, but total deflection, our criteria set is L over 240. So you could calculate 45 times 12 divided by 240. So 2.25, you can calculate 2.25 there, right? So, so this is actual service deflection check. I want you to just take a look at it, and uh, while you're just preparing the middle term, you need to show one typical detail, and you could just address, elaborate. I mean, PowerPoint, you show this, and okay, you can briefly elect a strength check, the maximum stress ratio for the bending. This case is 0.92 less than 1, so that it met, it's okay. And serviceability deflection check, right? Pre-composite and post-tension total, the deflection by using the camber, all deflections less than the criteria. So you need to conclude this, right? I'm gonna just skip the vibration from now because I think that's a little behind. But also you check some flange stress, okay? You check the bottom flange stress, which is less than. This one actually recently they added checking the bottom beam flanges stress. All right, so this calculation show this bottom flange stress is governing case. Maximum stress ratio is 0.997. Okay, right here, right? All right, so same thing. Can you close it and choose the Goddard as well? Choose Goddard, one of Goddard. Oh yeah, no, choose here. Yep, yep. So example. So this is single beam, simply supported beam. You need to choose one. Okay. Somehow it chose 21 by 50. Okay. Number of studs is slightly different, right? Number of camber is slightly different because obviously this one is pretty much the same. Nothing is different, but the span is relatively smaller. So this scholars, we have a 2-point load for 30 feet span, right? So same thing, you could calculate by hand. This one, if this is 64, wait a minute, 64 is maximum? Yeah, 64. Yes, it's a maximum sure. Okay, maximum sure. Oh, this is 64. Factor 64. So must be this is 32. 32. That's right. So if this is the case, this is 10 feet, 10 feet, 10 feet. Slightly off. Okay. Oh, this is bending. Yeah. 32. Okay, this is sure. Oh, okay. 64. Wait a minute. This is sure at the end. So this is sure means this is must be 64. Okay. Close it. Because we saw single beams there, the reaction is 64 caps. So 30 feet here, it's about 10 feet. So I think maximum bending roughly, if I calculate is 64 times 10. So 640. But they're showing 605, 605, 605. The reason why is they take some column dimensions off. So it's not 30. They take, because the Goddard is spanning from here to here, right? So they using length 30 feet minus whatever your column, the half of the column, half of column, maybe roughly 1 foot off. So they may use a 29 feet was main span, then 29 minus 10 between 10 divided by 2. So 9.5 times 64. Yes, so roughly 605, I got 608. So I think so these calculations, bending moment is based upon center, not center to center, because the column has dimension. Instead of center to center 30 feet, they're using at the face to face dimension. So girder span length is a little bit less than 30 feet. They use this length and calculate the bending moment here. Same thing, this capacity calculation is same thing, same as the what we discussed. They're checking also deflection, pre-construction, composite, post-composite. So you need to address that same thing. Girder, typical girder on 30 by 40. Your girder is 21 by 50. Number of stall, camber required 3/4 inch camber. The strength check, phase one and phase two, which all the stress ratio is less than one, and deflection check, the pre-composite 0.96, post-composite 0.5. When you add them up, so applying the camber subtract down, so maximum deflection 0.81 is less than your deflection criteria L over 240. So in this case is, let's say they're using 30. Yeah, they're using for deflection, allowable deflection L over 240, they're using center to center here. So center to center, 30 feet times 12 divided by 240. This is 1.5 inches. So you got 1.5. So same thing that ETABS, I think, give us a general strength and deflection check. And they show the lightest section on here, but you may be engineer, you may have engineering judgment. Okay, if using same depth girder, right, same beam here, you need to cope it. So let's say you need to cope this top and bottom, right? So both connection, right? So same depth, you need the top cope, bottom cope. So some industry, we're using a little bit deeper girder. We maybe choose 24 by 55. If architect doesn't have any headroom issue, right? The beam is 21. And girder is 24. Yeah, this case is we maybe only doesn't cope like all the way web member. Probably only we need to cut only the flanges here, right? Because a vertical web can go straight down side by, yeah, back to back of the shear step. So only if we can cut these flanges. If they using uh other maybe bolt connection angle connections, let's say if they using angle connections, yeah, sometimes some cases some detailer wants to use this, but somehow I don't like it too much. There's a sometimes they want to use a long angle to bolted connections so that you can avoid this coping, which means you're gonna deal with significant eccentricity, right? Here versus here, right? So this is something physical, the connections, how this connection is reflect on physical construction and the detail, but again, I want you to just take a look at it and discuss among your team player and just conclude. I mean, if you your teams doesn't want to develop, doesn't have time, use this model is okay. But if you want to add a few more bay and exercise, I think it's worth it too. Because you know, absolutely you need some time to invest on to learn uh new tools. It's gonna it's from now on your careers is all full of learning. I want you to enjoy learning some tool. Say okay. So I explain all. Hopefully this video, okay. I'm gonna upload it and cut it down. But I explained that two things. When you first time you run it, again, don't forget, go to design, because you need to override these sizes. Go to override, design, composite beam design. You need to, yeah, check the verify all member paths so that ETABS, yeah, these sizes, the new design sizes gonna be, you need to override over the previous auto selection property. So you're gonna keep the updated sizes. So that is the first, right? Second one is when you design it, you choose a one typical beam and girder and elaborate the design check that I described a minute ago. All right. So here, since yeah, we have a 10 minute, I want you to let's show you before you're gonna need it. So what after this? So we need to pull out the steel tonnage. Excuse me. Go to display. Go to show table. So let's see. Um, is there miscellaneous data? Can you check this guy? No, open it, open it. Click the plus sign. Okay. Okay, click the material list. Plus sign. Click the plus. Yeah. All right. So this is actually, if you check mark, check it, and ETABS give us the material quantity. Okay. So remember that miscellaneous data, material list. If you say okay, ETABS will give you the material quantities. All right. So far we are interested is concrete beam, the steel beam, right? We don't talk about column. So these are all steel. You have a total 95 kips. So the member steel tonnage, right? We didn't talk about any concrete. This is mostly a steel beam design. So concrete, no steel quantities 95 kips. If you check this, maybe pull down menu, you can yeah, there's a section based upon section profile. It give you the material quantity, number of piece, length, and weight. So obviously, when you sum them up, all this steel beam, this is I think 90 what 7 kips of steel tonnages, right? So you need it. I'm sure all of you learning some material well, take up as cost estimation class, but those are all material take up. You can put it